Okay, so today I'm going to talk about units of measuring brightness. There's things called radiance, irradiance, radiosity, radiant emittance, and so forth. So there's a discussion in the book, and as usual, I'm going to follow it pretty carefully. So the idea is we're talking about radiant flux. There's the first quantity, it's radiant power. So power is energy per unit time. Say it's measured in watts, which is joules per second, where joules is a unit of energy. And the idea is the energy we're talking about is the energy of photons flowing as light energy. And so every individual photon has its own energy, and you have a collection of photons that are crossing some place per unit time. Then it becomes power. And so the unit we use is capital Phi, is the notation for flux. And then irradiance is the flux incident on the surface per unit surface area. So if we have a piece of surface area here, A, and we have these photons coming from all directions and hitting it, and we measure how many hit it per second, that's flux, and then we divide by the area, then that's irradiance. So if these are sort of coming randomly, we would have half the area, we'd have half the flux, but we'd still have the same irradiance. And that means the notation for irradiance is E, and that's the flux that hits the surface over the area that hits the surface, or sometimes you talk about a little infinitesimal area, dA, and then you would say it's the infinitesimal amount of flux for that infinitesimal area A. So you could write it either way, depending on how big you think the area is. And then there's also flux that can be leaving a surface, going in the opposite direction. It could be light came in and reflected, or it could be something like a fluorescent bulb or any hot surface, like a hot stove, that's emitting light. And in either case, we have the radiant excitance leaving the surface. Another word for it that I'm more used to using is radiosity. Is the flux leaving. Again, per unit surface area. So it's the same thing. The book sometimes calls it M. I'm used to calling it B. And it's again the flux per unit area, or else a finite flux per finite area. Okay, now that really doesn't say how bright something appears. Because if you had the flux that was heading only in one direction, and that wasn't the direction you were looking in, the surface wouldn't appear bright. Basically, and another way to think of it is, suppose you're looking at the sun from Jupiter, and you're looking at the sun from the Earth. It's actually because space is empty and it's not absorbing any of the light, it's actually equally bright. It just looks smaller when you're farther away. So the amount of photons that come in your eye is smaller, but that's not because the sun doesn't look brighter, it's just because, you know, the angle of view from the sun is smaller. So we need to talk about something that accounts for that angle of view, and that's called solid angle. So I guess I need to define that first before we can talk about the flux per solid angle. So basically, let me go on this board. Suppose we have a cone of directions. It could be a cone to the sun from a certain distance, or it could be a cone of a strange shape to an eclipsed sun, right, which wasn't round. Whatever it is, it's sort of a subset of the possible directions from some point here, which is like the center of a sphere. And what we want to do is project that set of directions onto the unit sphere so that we're only concerned with the direction, not like how far this is or what area it is. So we get some sort of shape here that the cone projects to on the unit sphere. And then the solid angle say of a cone of directions from a point, I should say it's probably the area it intercepts on the unit sphere, with that point as center. So you could imagine the whole unit sphere. Does anybody remember what the area of a sphere of radius 1 is? It's actually 4 pi. The area of, actually we'll do an integral later on in the period which will be similar to that, but the area of the whole sphere is 4 pi. The area of a plane through the equator is pi, and because this is bulged up, it's actually 2 pi on the upper hemisphere and 2 pi on the lower hemisphere. It adds up to 4 pi. So the measure of solid angle is called steradians. It's like on a circle, if you have an angle here, and you measure that angle, this looks like about pi thirds, the length of this arc on the circle, that angle subtends, is actually pi thirds, and the total length of the whole circle is 2 pi if it's the unit circle with diameter 2 and radius 1. So analogous to that, they stay steradians for the 3D solid angle, and you measure it as area on a sphere instead of length on a circle. So now, if we have some surface here on a larger sphere, here this sphere had radius 1, but this larger sphere had radius r, then basically the ratio of this area to this area, what do I call this? Maybe this is area A1 and this is area AR. Right, so AR to A1. Right? If you go twice as far away, you're basically increasing this direction by a factor of 2 and this direction by a factor of 2. So the total area increases by a factor of 4. Right? So in general, if you take a figure and you make both dimensions multiplied by a factor of r, you're going to multiply the result by a factor of r squared. I'm sorry, it's an exponent. So that means the area, if you have anything on a larger sphere, and you project it down on the unit sphere, you're going to get the area on the larger sphere divided by r squared. So that's basically the inverse square law of light from the sun. If you're twice as far away from the sun, you get a smaller solid angle by a factor of 4. And we'll see that makes the irradiance smaller too. Now, what happens if, here I'm just going to draw a 2D picture. And suppose I have, say, a distance to this vertex of a polygon or an area. But that area isn't squashed flat on the sphere. What I'm going to do is say, what happens if I project that area perpendicular to the sphere? So let's take this farther away point for now, and we'll project it onto a tangent plane of the sphere like this. And what I'm going to do is I'm going to project it in a parallel way. So how should I do that? I should probably say, let me make the paper like it looks, picture like it looks in my notes instead. Sorry for doing this. Here is the area. Maybe I should make it a little more clear, the bigger angle. This is tangent to the sphere, and this is a different area that isn't tangent to the sphere. And I want to project it perpendicular to this tangent direction. Let's see, maybe it's a little bit complicated. This figure looks messed up because really the solid angle it subtends corresponds to this arc here. And I want to say for a small opening angle, it's really directly related to this parallel projection onto this straight line here, tangent to the sphere. So maybe what I should do to convince you that that's true, because in this picture it certainly doesn't look like it, is that as this ratio of this size to the radius of the circle gets smaller, it's a better and better approximation. So, because now I'm not even convinced, although I was when I was writing the notes. Suppose I have something like this, and here is the tangent thing, and here is my tilted thing, and I think of, well, here I could, if the center is way down here, and I project it like that, from this vertex instead of the vertex where it's tangent to the sphere, then I guess I can, what I want to do is say that this length projects onto that length, and then this length is very close to that curved length. And it'll get closer and closer as this sort of angle between these two rays gets smaller and smaller. So I guess what I'm interested in is the angle between, so I guess this thing is a right angle, and I'm interested in this angle between this radius vector and the normal to the surface. And that's the angle that I'm calling alpha. Right? Since this normal to the surface makes a right angle, and since the radius direction to the tangent direction also makes a right angle, I guess I'll write that, maybe that right angle this way, then this is the complement of this angle, and so is this, so they're equal. So if alpha is the angle here, then if I have this line segment, I'm only doing a circle, then I can say here is A, and then this area, this length, say, will be A cosine theta. And now if I consider a sort of an area also in the blackboard, but in a direction which is perpendicular to the direction to the center of the sphere, and goes into the blackboard that way, so we're only seeing a cross end on, then that into the blackboard dimension, when you project it, will be approximately the same. Right? If it's again, it's sort of the difference between a line like that and a line like that. And so it's the area, the ratio of these areas will be cosine theta. Okay, and now my claim is that this area is approximately the same as this area because this is tangent to the sphere. And so if it's a small area, the distortion you get by this slight curvature goes to 0. So what that says is that a generalization, if we go back to this formula, it's A, whatever that area is, times cosine theta divided by r squared. And now it's not an area on the sphere, it's an area, say a flat area, little piece of polygon in any orientation, and I wrote theta. What I really mean is alpha, the angle between the surface normal and the radius direction. Okay, so now maybe I can go back to this board and define radiance. Where's my page 1 here? Radiance is how bright something appears. And that means it's flux per solid angle per unit area. Right? So suppose I have a beam of light coming from the sun, and I hold this piece of paper so it's perpendicular to the sun's rays. So I get flux per unit area on the surface coming in per solid angle. Right? Then when Jupiter, if I move much farther from the sun, say twice as far, the solid angle will get a quarter as big. And the amount of light, the irradiance, will be a quarter as big. But the radiance will be the same because it's the flux per solid angle, and I'm dividing by a smaller solid angle. So the radiance is the flux per unit area, say normal to the beam. So I always want to measure the flux per area normal to the beam. If I have, say, flux coming this way, and here is the area normal to the beam, but I actually tilt my piece of paper so it's more like that, right? Then the same flux will hit both, but this area here, I guess picked like that, is actually larger than this area. And I don't want to measure it per unit area on the larger surface. I want to get it perpendicular to the beam. And that's what this normal to the beam is, per solid angle. So I said solid angles are measured in steradians, but it's really a pure number, right? It's an area on the unit sphere, and since the radius is 1, it just comes out to a number. So let's see. Let me go back to this board again and write a formula for it then. So the notation we use for radiance is L. And what it is the flux, well, let's use the D, with d omega dA perpendicular, where d omega is a flux, d phi is the flux, d omega is one of these solid angles that the flux is coming from, and dA perpendicular is the area perpendicular to the beam. And if I draw that picture I drew on the other board again so I can reach it here, here's the beam going this way, and here is area that isn't perpendicular to the beam. What I have to do is find out the equivalent area that is perpendicular to the beam. So again, I need the normal to that area, which is, I don't know, it's hard to draw a right angle, pointing out like that. That's the normal to the actual area that's intercepting the beam. And I have an angle between that normal, this is a right angle now, and the beam direction. So the beam is, say, coming here. So here's the beam direction, and this angle is theta. I have the same kind of picture I was drawing before, right? I'm confusing it with the 3D picture. Let's just draw the 2D picture of the sort I had before, where here is an area, and here is its normal. And here's the direction that the beam is going, and that I'm also projecting it onto this area. And this was my, now I'm going to call it theta instead of alpha, because that's what the book does in this context. Because this is perpendicular to the surface, and this is the surface that, this n is perpendicular to this surface, and the beam direction is perpendicular to the surface normal to the beam. This is also theta, and so this dA perpendicular is dA times cosine theta. So I can write this as the flux per unit solid angle, and then times the area per unit area, but I have to multiply that area by cosine theta to get the unit area normal to the beam. And in the book, they put a d squared here because they say, well, it's a doubly small quantity if the solid angle is small and the area is small. So, remember, did I erase it? Irradiance, I guess I did, right, was under here. The irradiance was the flux per unit area. So I can relate it to radiance times solid angle. If I multiply by d omega and cosine theta, I will get L d omega cosine theta equals the flux that actually intercepts my area that isn't normal to the beam. And so this is sort of the cosine theta factor you get in Lambert's law, where a diffuse surface emits light proportional to how much light hit it. And how much light hit it is, we have to multiply the brightness of the light by the solid angle. That's what I keep comparing, like the brightness of the sun is constant, but the solid angle is smaller when you get farther away from it. And so a radiance times the solid angle says how much flux is coming per unit area normal to the beam, because you already multiplied it by the solid angle, canceling out this per solid angle. And then that's equal to the irradiance E. And then for a perfectly diffuse reflecting surface, the light that comes out is proportional to the irradiance. Okay, so to actually do something like Lambert's law, we actually have to integrate over solid angles here. And so what I want to do is talk about solid angles in spherical coordinate system. So if we have a sphere, let me draw the big sphere here, just like on the other board. Here's the equator, and here's the radius, and I guess this line of the equator should be dotted if it's back in the background, behind the surface of the sphere. And now let's say this is the north pole of the sphere, and I'm looking at spherical coordinates. So actually that line, let me just draw this vertical line as thicker when it pokes out of the sphere and thinner without making it dotted when it's inside. So around the North Pole, we have all these arcs of longitude. Right? And they intersect the equator in a certain point. Say the x-axis intersects the equator at this point here. And this is the z-axis, and the y-axis intersects it somewhere there. And now what I want to do is I want to measure, for any point on the sphere, I want to measure two angles. One angle measures how far away the line to that point here is. See, the point is some 3D point on the unit sphere. Or actually, it could be a sphere, a point on any sphere. Because spherical coordinates say the radius of the sphere is r. And then the angle away from the North Pole is called theta. And then the angle around the equator, right? The fact that this thing went through this x-axis plane is purely coincidental. Let me make it so it doesn't, because it's sort of confusing if it does. Let's say here is the point here. So this angle now is theta, and now what we do is we come either down to this arc or we just come straight down in the plane through the z-axis, the North Pole of this point here, and we get an angle, right? This is the vertical projection, and this is sort of continuing that longitude line. However we think of it, this angle phi, measured from the x-axis, is another coordinate. It's basically like latitude and longitude, except that I think longitude, if you look at the sphere on the inside from the outside, I don't remember whether you're calculating clockwise or counterclockwise from Greenwich. And the North Pole latitude is 90 degrees. We're like going to count at 0 and go down here to pi. And then from the x-axis around this way to 2 pi. And so we can have spherical coordinates. Basically, what we need to do to find the x and y is we have to have the length of this vector. It's the same as the length of that vector if I draw it parallel here through this point P up to the axis. And this length is equal to r times cosine theta, right? Because theta is measured from this z-axis, not up from the equator plane. So actually then it's not cosine theta because it's measured from the z-axis. This is actually r sine theta. Because this is the side opposite multiplied. The ratio of the side opposite to the hypotenuse is sine theta. So you multiply the hypotenuse by the sine theta to get the side opposite. Okay, so now we can find the x coordinates of this point to say that we have this vector of length r sine theta, and it's turned phi degrees away from the x-axis, right? And that means the x-coordinate is going to be cosine phi times that r sine theta. Maybe I'll write it this way: r sine theta times cosine phi. Because if you're in the xy plane and you have a vector that makes an angle theta here, then whatever this length is, this length, say this is L, this is going to be L cosine theta, and this cosine phi, I guess this is phi now, and this is L sine phi. And L was our r cosine theta, the length of that projection of the vector from the center of the sphere to the point P on the xy plane. And y equals the same length, L, r sine theta sine phi, and z equals r cosine theta, right? Theta being the angle away from the North Pole. Now the side adjacent to the hypotenuse is the cosine theta. So that's spherical coordinates, and on the unit sphere, you could just make r equals 1. So now let's see. My picture is a little bit complicated, so let me draw it again here so I only have a little piece of this area. What I want to see is what is the area if I let theta vary by d theta and phi vary by d phi. So how can I do that? Let me draw sort of a magnified view of a part of this sphere here. Here is the North Pole. Here is the x-axis. And now what I'm doing is I'm going to make a sector whose width is d phi, some angle here. And that's sort of a small amount of longitude change. And then I'm going to have a small amount of latitude change. So let's see, how can I draw that? There's actually smaller circles up here, right, that are similar to those ellipses. And I'm at two different latitude lines. So say here I have a point P as a function on the unit sphere. On the general sphere, our coordinates are r, theta, and phi. And on the unit sphere, they're just theta and phi, because the r is 1. And so here's my point depending on theta and phi. And now I want to let phi increase by d phi, and theta, which is sort of this angle here, be d theta. Right? That's along these longitude lines. So the question is, what's the little area? This is almost like a rectangle. And in fact, this arc really is of length d phi. Right? Because this is a unit circle. And I said at the very beginning, the arc length on the circle is really measured by that angle. But this circle isn't a unit circle. Right? We just finished computing that its length is equal to r, where was it? R sine theta is this radius. So if we have a circle of this radius and we go by a d phi in here, let me make the same mark. There's no room for the letters, so I'll just try and indicate it by arrows pointing from both sides. D phi is this little angle. Then this piece of arc has length r, well, the length is 1, right, because it was a unit sphere. So it's just sine theta d phi. So the dA on the unit sphere is sine theta d phi, right? If I multiply this d phi by this sine theta, I'm sorry, did I do this wrong? This is sine theta d phi for this part, and this one is d theta for this part. I wrote that wrong, and nobody corrected me. Right? Because theta is measured down here. This is along the longitude line, and this is along the latitude line, which is not a great circle. It's a smaller circle. That's why you have the sine theta factor. Does that look familiar for anybody doing spherical coordinates and solid angles? Okay, so let's see. Maybe I'll go on this board. And now I want to talk about not light just coming from the sun, but light coming from all directions. If you're outside, you might compute an environment map which has the sun in the skies and a tree and the buildings around you. And you may have a piece of surface, and you want to know, to figure out how bright it looks, you have to know the total irradiance coming onto the surface, not just from a small light source, but from the whole hemisphere. So the total, here is a surface area, and at each point x on the surface, say the area is A, we consider a unit sphere, but actually, if we're assuming the surface is opaque, stuff coming from below the surface isn't going to get through it. We're really only interested in this stuff coming from the hemisphere above. So omega equals the hemisphere at x, centered at x, above the surface. And the total flux, right, d phi was the radiance times d omega times dA perpendicular, which was, say, dA cosine theta. And theta, here's the surface normal, is going to be the north pole of the sphere. And this theta, the angle between the incoming light and the surface normal, actually, we can think of theta as the direction, not the direction the light is flowing in, but the direction pointing to where the light is coming from. Then this really is the angle between the surface normal and the direction the light is coming from. So this formula was the definition of radiance, but now I'm turning around saying if I know the radiance, then, and I know a piece of small solid angle and a piece of small surface, then I can get the flux. So that means the total flux hitting the surface is the integral over the surface for the dA part times the radiance, and we can say the radiance depends on the position and this angle, omega of, well, let's see. Right now, capital theta, small theta is the angle between this unit direction vector, capital theta, and the North Pole. And capital theta stands for an actual 3D unit direction vector. Well, so maybe I just call it theta. Put a capital theta in here. dA cosine lowercase theta, which is one of the two components of specifying capital theta in these spherical coordinates, d omega of this capital theta. And in fact, the way the book writes it, and then I have to also integrate with respect to d omega over all this hemisphere, because I'm trying to include the light that comes on the whole hemisphere. So the way the book writes this thing, instead of the radiance at x in direction theta, they say the radiance for light from direction theta flowing toward x. So they just put an arrow here. And that says the light is hitting point x coming from direction theta. So now I can say the irradiance should be this flux over the area. So now if we assume that this is now, maybe I'll say d phi over dA, where now this is the integral similar to what I have here, but for a small area where the flux, the area is so small that the flux really doesn't depend on this position x. Right? Then I can take my integral over area, and it'll just be, well, let me assume that if things are constant, then this integral over the area will be dA, and I'll just have the integral over the solid angle. So let's see, how would I say it? d phi, let's write it like this. For a small area, it's the integral. We can assume things are constant under the integral as a function of the position x on the area, and take that out of the integral, and then it just becomes L. I'll use my notation instead of the book's notation, because that's what I have in my notes. Cosine theta d omega. And then the irradiance, which is d phi d flux over dA, is just this integral over the solid angle hemisphere of L. And here maybe I'll use the book's notation. And the book's notation, they write d omega, d solid angle for this direction, theta. The only way I can make my capital theta is different is sort of make serifs on my little horizontal bar. That's what I'm trying to do. And this is a capital phi too, as opposed to my lowercase phi, which is just curly without serifs. Okay, so now this integral just says to get the irradiance, you integrate this cosine weighted solid angle, the cosine theta for the foreshortening, right? Because if the surface is tilted with respect to the beam, then you have a larger area on the surface than you had normal to the beam. And we integrate it over the hemisphere, and we get the effect of the light coming from all directions onto the surface. Okay, and similarly, we can say the light leaving a surface, the total light leaving a surface at a position is the integral of omega of now the light radiance leaving the surface. So if you talk about leaving the surface, we say starting from point X headed in direction theta. So this notation says now the light's actually starting from the point X and about going away from the surface. And so that is how bright the surface appears. And now we still have the cosine theta d omega of capital theta. Because, again, if here we have a surface and we have light leaving in this direction, well, the radiance is going to be brighter by the factor of the ratio of this area to this area, right? Because the same light is on a smaller area. But if we want to know this radiosity is the light leaving per unit surface area. So if it's leaving from a larger surface area, it's actually less than the radiance by that same cosine factor. It's the same argument with just the light flowing in the opposite direction away from the surface instead of toward the surface. Okay, so I have about 8 minutes left. And I think I can actually do the case of the irradiance when the light comes equally from all directions. So before I said, well, let's take the area small enough so that the light doesn't vary out of it and take that area out of the integral and just turn it into dA. Now I want to assume the light at position X omega is just a constant L, independent of omega. So this is for a diffusely emitting surface. So if the light looks equally bright in all directions, from what I just finished saying, it's not actually equal amount per unit surface area flowing out in all directions. Because of that foreshortening factor, it's actually, if it looks equally bright, it's still actually less per unit area leaving on diagonal directions than they straight up normal to the surface. But because of the foreshortening effect, it appears equally bright in all directions. That's what a diffuse emitter looks like a very rough surface. And then if we want to compute the radiosity from the surface, just from that brightness, so my integral is now the integral over the hemisphere of just constant L times cosine theta d omega of the solid, this capital theta leaving on the unit hemisphere. And so now, if I haven't erased it, what I need is my formula for d solid angle, right? That dA on the surface is really my d omega from a small solid angle, like with a d theta and a d phi. Because I want to turn this integral into an integral, say, from 0 to 2 pi d phi, and an integral from 0 to pi halves d theta of L times cosine. Right, this is basically what I'm saying is this d omega h is going to be sine theta d phi. That's what I had on the other board for solid angle measured in spherical coordinates. And I'm going to need spherical coordinates to do this integral because it's got the cosine theta, which is a spherical coordinate. So basically I have cosine theta sine theta. Right, so I've turned this area d omega into a double integral, and my d theta, d phi, sine theta make my d omega, and then the L cosine theta is right here. And now I could take L out of this integral as a constant, and also this part here doesn't depend on phi, right? It only depends on theta. So I can integrate this d phi as just 2 pi. And then what I've got to do still is the integral from 0 to pi halves of cosine theta sine theta d theta. Right? My d phi just made my 2 pi here because it's a constant time. It's a thing that doesn't depend on phi times d phi. So I just need this thing. So now let me see if I can finish that integral in 3.5 minutes. So what I want to say is that d theta of sine squared theta over 2, the derivative of sine squared is twice times the sine times the derivative of the sine, right, by the chain rule. What's the derivative of the sine? Cosine. Right? So I found something whose derivative is this thing I'm trying to integrate. So what that means is the integral from 0 to pi halves of sine theta cosine theta d theta is this quantity here, the antiderivative sine squared theta over 2 evaluated between 0 and pi halves. So what's sine of pi halves? Sine of 90 degrees, right? It's 1. And so the upper limit is a half, and sine of 0 is 0. A half minus 0, which is a half. So that means that this integral is a half. So I have 2 pi L times a half, which is pi L. So what that says is if the light is exiting equally in all directions, then the actual complete radiosity is pi times, is pi times the radiance. So I have about a minute left, or a minute and a half. I probably shouldn't erase this. Well, maybe I'll stop here, because I did want to take a vote today. I remembered now. I was going to ask you how many people. Well, I'll pose the question first, then I'll ask how many. The question we're trying to decide is whether I'm going to do the last few lectures or part of the credit is going to be from people presenting the papers that cover, the original papers that cover the material near the end of the book and some stuff that isn't in the book. Advanced topics once we do the basic homework. So how many people want to take turns presenting research papers as part of your grade near the end of the quarter? And how many people want me to present the material instead? Okay, well, that decides it. I'll lecture the whole quarter. And you'll probably have other graduate courses, more advanced courses, where professors will ask you to present papers without asking your opinion on whether you want to or not. Okay, so that's it for today.